Hi, I'm Ronit Rubenfeld, and I'm a professor at MIT. There's been a huge hubbub about big data, but what I want to talk to you about is what do you do when you have really big data? So big that there's no time to look at it all. What can you possibly hope to say about data that you can't even view? Let's take an example to be concrete. Let's take the famous small world phenomenon. We'll model a social network as a graph. We'll associate with each person a node, and we'll place an edge between pairs of people that actually know each other. And the 6 degree of separation property that Millman first studied, was later a subject of a Broadway play, and then became even a movie, asks if all pairs of people are connected by a path of distance at most 6. So you see in this graph, this guy is not connected to anybody, so this graph does not have the 6 degree of separation property. So this illustrates the problem we have with really big data. It may be impossible to access some of the data, and even what is accessible is so enormous that no single individual or even reasonably sized group of individuals could hope to access all of this data. And even what you can access as a group is so large that by the time you access it all, the data might actually change. So in our small world example, somebody could die, somebody could be born, things could change. So this illustrates the problem we might have with the standard notions we teach in undergraduate algorithms courses. We teach that the goal is to get a linear time algorithm. Once you get a linear time algorithm, that is, an algorithm which on inputs encoded by n bits or words takes at most a constant times n many time steps, we teach you that when you get this, you're done. You get a gold star, A+, and you can move on to the next problem on the exam. But maybe this notion is inadequate for big data. But what could you possibly hope to do if you can't even see all of the input data? You certainly can't answer the same types of questions that we had hoped to answer before. Any question that has a for all or an exactly type statement in it is going to be hard for us to solve. We're not going to be able to answer exactly how many individuals on Earth are left-handed. We're not going to be able to answer whether all individuals are connected by at most 6 degrees of separation. So we're going to have to make some compromise. Okay, so the compromise that's traditionally taken by the statisticians is to approximate. Let's approximately determine how many individuals on Earth are left-handed. And this is a well understood, all the sampling bounds and polling bounds. We use this to determine who's going to vote for which political candidate. We use this to determine if a certain type of drug is working on a certain disease. So this is something that's classically studied and used all over. But because of the types of data that have now appeared are much more interesting and have certain kinds of structure that we're looking for, the questions that are now arising are quite a bit different than those that have been classically studied. So in particular, for the 6 degree of separation property, we might ask, is there a large group of individuals that are connected by at most 6 degrees of separation? You might ask, are at least 99% of the individuals on this Earth connected by at most 6 degrees of separation? So what types of approximation or compromises are we looking for? We're going to talk about two in this module. We're going to talk about property testing. We're going to try to distinguish data that has a certain property, such as networks that have 6 degrees of separation, from data that is far from having the property. Networks where not even 50% of the population has the 6 degree of separation property. And we'll define what that means. We'll also talk about classical approximation problems. We're going to try to approximate the correct output of a computational problem. The computational problem might be the classical statistics problem of estimating how many people are left-handed on this Earth, or it might be something more interesting, like approximating some solution to a combinatorial optimization problem. So we've seen that we're going to have to make some sort of compromise. We've talked about two types of compromises that we might make. And in the following segments, we're going to see how and when we might apply these types of compromises to specific questions. So in the past segment, we saw that we're going to have to make some compromise. And in this segment, what we're going to look at is the property testing compromise. We'd like to distinguish data that has a certain property from data that is far from having the property. Okay, so it's a little bit different than the way we usually ask questions. Normally we ask if it has a certain property or not, but here we're going to give a little leeway. Okay, so if you let this big gray rectangle be the set of all inputs, and inside we'll say that this yellow oval is inputs that have the property, here you want to say, yes, they have the property. Okay, our algorithm has to pass these inputs. It has to say, yes, these guys have the property. Here, we want to say, no, they do not have the property. But these purple guys, yes or no is a perfectly fine answer because they don't have the property, so it's perfectly fine to say no. But on the other hand, they're pretty close to having the property, so it's not the worst thing in the world if we said, yes, they do have the property. Okay, so we have these purple inputs where we don't care what answer the algorithm gives, and this leeway allows us to design much faster algorithms. Okay, so that's why we might want to look at property testing. You can do it so cheaply. And a lot of times that's the natural question to ask. For example, if you know there's noise in the problem anyway, why would you want an exact answer? And if the data is constantly changing, it's never exactly going to have the property or not have the property. It's always going to be either close or far. Finally, it can give you a fast sanity check. If you have to perform lots of these tests, at least the really bad inputs you can get rid of quickly and spend the rest of your processing time on the finer distinctions. And finally, it's related to the model selection problem in machine learning. So what types of properties might we look at? Well, we could look at any type of property of any type of object. We could look at properties of functions. Is our function a linear function? Is it a convex function? So what properties are we interested in? We could look at properties of any object and any type of properties of these objects. So we might look at whether a point set is clusterable. We might look at whether our graph has small diameter or 6 degrees of separation property. Or we might ask, is the graph even connected? Is a list of numbers in increasing order? Does it have small edit distance to another string? Are we close to a code word? And lots more properties. Whenever we do solve a property testing problem, our model has to specify how do we represent the object and what are the allowable types of queries. Then we must define what we mean as a notion of close and far. For example, we might say that two graphs are close if you can delete a small fraction of the nodes in one graph to make it look just like another graph. Or you might say that a string is close to another string if you can delete a small fraction of the entries and then they become identical. Okay, so the notion of close and far is specific to the object that we're looking at, and you have to define it each time you define one of these testers. So what are examples of things we can test? Well, in our 6 degree of separation property, we can test if a social network has 6 degrees of separation or is far from having 6 degrees of separation in constant time, independent of the number of people in the network. So that's something we can do quickly. We can also test if a large set of data points are clusterable in constant time. Again, independent of the number of points in the data set. So this weakening of what we're asking of the algorithm is really helping us to get much faster algorithms. How do we construct a property tester? We need to find a characterization of the property that is both very efficient to test and robust in the following sense. We want that objects that have the property satisfy the characterization that we're going to be testing, and we want that this characterization doesn't allow bad objects to pass. In other words, objects that are far from having the property, they should be unlikely to pass. And our tests are going to be randomized, so we're never going to have perfect probabilities of error, but we can make our probability of saying the wrong answer as small as we like. Showing that objects that are far from having the property are unlikely to pass is usually the bigger challenge. So how would we go about constructing a good characterization? So let's start with a bad testing characterization for 6 degrees of separation. Here we have, for every node, all other nodes are within distance 6. So what's bad about that? That's a perfectly good characterization of 6 degrees of separation. But this is a really bad characterization, because how are we going to test that for every node, all other nodes are within distance 6? We're going to have to run through every single node in the graph and then compare it to all other nodes in the graph. That takes forever. Okay, here's another bad one. It's going to fix the first problem, but not the second. We can just test it for most nodes. Now we can just do random sampling and make sure that most nodes have the following property, that all other nodes are within distance 6. Okay, so this part's not a problem, but we're running into a problem here. Because how are we going to test that all other nodes are within distance 6? There's too many. But here's a good characterization. How about testing that for most nodes, say 99% of the nodes, there are many other nodes within distance 6. And it turns out many is small enough that it's very doable. Many is actually something on the order of 10 or 20. It's not a big deal. And most is, we have to check that 99% of the nodes have this property. So, a few hundred samples would be good enough for us to do this. This is something we can do much faster than looking at all the nodes in the graph. So we're talking about doing a number of tests that's on the order of a few hundred instead of having to look at a network that contains as many nodes as the people in this world. Well, many other properties have been studied on graphs, functions, point sets, strings, and there has been a lot of exciting work in this area in recent years. There are amazing characterizations of the problems that can be tested both on graphs and functions that can be tested in constant time independent of the size of the input. In the next segment, I'm going to talk about more traditional approximation problems that can be solved in sublinear time. Okay, so in this segment, I'd like to talk about sublinear time algorithms that perform classical approximations. Here, the goal is to output a number that's close to the value of the optimal solution, but since we're running in sublinear time, there's not going to be enough time to construct a solution. So some examples of problems that have been considered are sublinear time algorithms that approximate minimum spanning tree, vertex cover, max cut, positive linear programming, edit distance. These are just classical problems that have been well studied in our community, but now we're approaching them from the sublinear time perspective. Okay, so before I get into it any further, we'd like to talk about what we mean by an approximation. So there's two notions of close that we're going to discuss. We could talk about an approximation being a C multiplicative approximation if we output a number that's within a multiplicative factor of C of the best solution. So we might want to output something that's at most C times the optimal solution. We might also discuss a C additive approximation. Here we'd output a number that's additively within C of the best solution. So here our output should be at most the optimal solution plus C. So here's an example, the vertex cover problem. Here we're given a graph, and let's take this graph. A vertex cover is a subset of the nodes that touches every edge. So we have to touch all 4 of these edges. So here's an example of a vertex cover. This is a vertex cover of size 2. If you look at this graph, you'll see that there is no such thing as a vertex cover that has only one node in it. And the question we're going to ask is, what's the minimum size of a vertex cover? So this is one of the classical NP-complete problems. There's, however, a polynomial time multiplicative 2 approximation based on the relationship of vertex cover and maximal matching. So I'll say more about that in a minute, but what this means is even though we can't find the minimum size of a vertex cover, we'll never output a number that's more than twice as big as the minimum. Okay, so it's a pretty good approximation. What we're going to see here is that we can get a really good approximation for vertex cover on sparse graphs, and the running time of our algorithm is going to just be a constant time completely independent of the number of nodes in the graph. So we're going to output y, which is at most 2 times the optimal answer, but we're going to have a little bit extra additive error. So we're going to have this extra epsilon n additive error, and that's because we're going to have to do some sampling. So how are we going to do this? We're going to use the oracle reduction framework. And we're going to assume there's some sort of oracle that has in its head a really good vertex cover. So it's no more than twice as big as the optimal vertex cover. Okay, so this thing is going to be able to answer us queries of the following form. We're going to ask it, is node U in your vertex cover? And it's going to say, yeah, node U is in my vertex cover. And then we'll ask, is node V in your vertex cover? And it's going to say, no, it's not in my vertex cover. So we can ask node by node questions. And we're going to use this oracle plus standard sampling to estimate the size of the cover. So what we're going to do is just pick random nodes and ask the oracle whether these random nodes are in the vertex cover or not. And by estimating the fractions of times that the oracle says yes, we're going to have a good idea of how many nodes are in the vertex cover. But that is why we need this epsilon n additive term, because we are using sampling at this point. So that's where that comes in. And this factor of 2 comes in because the oracle doesn't actually have the best vertex cover. We can only expect that it has a factor 2 approximation to the vertex cover. Okay, now this is all great, but how do we get this oracle? I mean, that's sort of magic. And it turns out that we can actually get this magic in constant time. So there's actually 2 approaches to this. So one approach would be to sequentially simulate the computations of a fast distributed algorithm. And this is an approach that's taken in constructing many sublinear time approximation schemes. But I'm not going to actually talk about that today. What I'm going to talk about is an approach that tries to figure out what the greedy maximal matching algorithm would do on the node U, because we're using the greedy maximal matching to construct a good vertex cover. And if we can figure out what the greedy maximal matching algorithm does on U, then we're done. So to do that, I have to explain to you how we use maximal matching to get a good vertex cover. So what is maximal matching? Well, a maximal matching is a subset of the edges such that no node is in more than one edge. So you could think of people, and you could put edges between pairs of people that like each other and are willing to get married. And then you put edges in the matching if those people agreed to get married, but you want to make sure nobody gets married more than once. Okay, it's okay to have people that didn't get married at all, but it's not okay to have people married to more than once. Okay, so think of that as your matching. And M is maximal if nobody else can get married. Okay, if anybody else gets married, then you've broken the legality issue. Okay, so a well-known fact is that nodes in any maximal matching would give you a pretty good vertex cover. So all you need to do is find a maximal matching, and it turns out that what you do is you put all nodes matched by the maximal matching into your vertex cover, and that is going to give you a factor 2 approximation to the best vertex cover. So the beauty of maximal matching is a very simple greedy algorithm can be used to find one. Okay, so all you need to do is, and now I'm not talking about a sublinear time algorithm, just a standard algorithm. This is the standard greedy algorithm. Just look at the edges in any arbitrary order. It doesn't matter. Okay, so go through the edges one by one. And when you go through edge UV, you look and see, have U and V previously been put in the matching? If they have not, then they can legally be married. So add this edge UV to your matching. Okay, if either of them was already previously married, then you can't put edge UV into the matching, so don't. Okay, so you run through every single edge, put the ones in that you can, and output this matching. Why is it maximal? Well, if you decided not to put the edge UV into the matching, then either U or V had to already been matched. Okay, so that gives you a nice maximal matching. It's a very simple algorithm. Okay, so now what we want to do is figure out whether a specific edge E was put into the matching by the greedy algorithm, but we don't want to run through all the edges in order to figure out if edge E was put in the matching. So good news, you only have to look at edges that came before edge E in the matching to figure out if E is placed in the matching. Okay, I want to know if E is placed in the matching. I need to look at anything adjacent to it, any edge that shares a vertex with it, and see were they put in the matching. And if none of them were placed in the matching, then neither of U's endpoints were matched previously, so you're going to end up placing E in the matching. Okay, so you need to know if adjacent edges that came before E in the ordering are in the matching. You don't need to know anything about edges that came after E. Okay, so this sounds like it might help, but you still could have arbitrarily long dependency chains. So let's just take this very simple graph of the line, and let's look at this edge here. How do I decide if that's in the matching? Well, edge 112 came before edge 113. I don't need to check and see whether 113 was placed in the matching. I know it wasn't, because it comes after me in the greedy ordering. But I do need to figure out, was 111 placed in the matching? Because if 111 was placed in the matching, then 112 cannot be. Okay, but to figure out 111, I have to figure out 110. To figure out 110, I have to figure out 89, and so on. So that's my problem. And essentially, I could have this arbitrarily long line, and I need to figure out if I'm an odd or even number of steps from the beginning. Okay, so that seems a real pain to do. But the idea that works here is just assign a random ordering to the edges. Greedy works under any ordering. The random order can be shown to have short dependency chains. So it's a really beautiful algorithmic idea. It gives simple algorithms with really fast running times. And moreover, it's quite general. So you can use it plus some more complicated algorithms to get good sublinear time approximation algorithms for other problems as well, such as sparse maximum matching, set cover, positive linear programming, and a number of other problems as well. So you can get even better results for special classes of graphs, including planar graphs. These would be better in terms of the approximation parameter. So we've seen a beautiful idea that allows us to get simple algorithms that run in constant time and give us really good approximations of many combinatorial approximation problems. So up until now, we've been talking about the case where we have big inputs, but the answer we output was just a number or a pass-fail type indication. What happens when the computational problem also has a very big output? Maybe we don't actually need to see the whole output. Maybe we just want to see small portions of the output. Do we need to see all the input? Do we need to solve the whole problem in order to get the ith bit of the output? So let's take some concrete examples. Suppose my input is the encoding of a very big message. Now, I'd like to decode this message. So the output of my decoding algorithm is going to be the original big message. But in fact, I don't actually need the full original message. What I need is just the ith bit of the original message. Do I need to decode the whole message in order to figure it out? It turns out that you can design codes, and they're called locally decodable codes, so that very few queries to the input are needed in order to figure out what the ith bit is in the decoding. A similar idea works for local decompression algorithms. In this case, the input is the compression of a very large piece of data. The output of the decompression algorithm would be the original of big data, but I don't want the whole original data. I just want to know what's the ith bit or word of this original data. And it turns out that you can design compression schemes so that they both compress well and few queries are needed to compute the answer to such questions as what's the ith bit. So this led us to propose a new model of local computation algorithms. Here, our input is huge, but it's written down. And we'd like to compute the output y, but we don't actually need all of y. What we need is to be able to answer queries such as what is the I1st bit of y? What is the I2nd bit of y? So we're going to assume there's some local computation algorithm that is allowed to access the big input x, and it's just supposed to tell us, whenever we ask it a question, what is the value of y at bit I sub 1. So it tells us y I sub 1 when we ask it about I sub 1, it tells us y I sub 2 when we ask it about I sub 2. So the models of locally decodable codes and local decompression algorithms can be put into this model, but what more can be done in this model? Well, it's a relatively new model, so there's a lot of research left to be done, but we have found a few non-trivial examples, such as maximal independence sets, certain constraint satisfaction problems, various graph sparsification type questions, and local algorithms for ranking web pages, graph partitioning, and even some type of data reconstruction questions. One hope for these LCAs is that you might be able to use them in the cloud. So there's some input X written down, and there's these independent local computation algorithms running around, but not talking to each other. And you could imagine clients at different locations asking their copy of the local computation algorithm, what is the value of y at certain locations? And these local computation algorithms can run around giving consistent answers without actually having to solve the whole computational problem. So the LCA model has just been proposed in the last couple of years. There are quite a few recent results in this area, and we think this is an exciting new direction for research. Up until now, we've been talking about the case where the data is written down. But I'd like to turn to a different model. And this is the case where the only way you can access your data is via random samples. How many samples of the data do you need in order to understand your data. Distributions arise in every scientific and economic endeavor, but let's just take an example of the lottery. If you want to play the lottery, wouldn't you want to know that the lottery's fair? For example, if you look at the websites, it would seem that maybe some of the lotteries are not so fair. Some websites claim that you can predict future winners. In fact, there's a true story. There's the Polish lottery, Multilotek, which is actually a machine that had a bunch of balls in it, about 80 balls. And what the lottery did is choose uniformly at random a distinct 20 balls out of the machine. Okay, so these are 20 numbers chosen at random from 1 through 80. But the problem was the initial machine was biased. So the probability of the numbers 50 to 59 were too small. And when people figured that out, they made a lot of money. They just didn't bet on 50 to 59. Okay, so it may be possible that your lottery is not fair. Now, in this lottery, you could see it because there were only 80 balls. Every time they took draws, they took 20 out of the 80 balls. You could see how many times they showed up. So basically, every number showed up multiple times, and you could get a really good estimate for every ball, how often it got pulled out of the machine. But let's take another example. The New Jersey Pick 3 or Pick 4 lottery. What do you do there? In the New Jersey Pick 3 lottery, you pick 3 digits in order, 0 to 9, 0 to 9, 0 to 9. So that's 1,000 possible values. And in the Pick 4 lottery, there's 10,000 possible values because you're picking 4 digits in order. Okay, so let's even assume that every time you pick a new number in the New Jersey Pick 3 or Pick 4 lottery, it's actually chosen from the same distribution independently of previous days. But I just want to know, is this distribution uniform? Okay, well, let's try it out. So we did this test a while ago. In the Pick 3 lottery, there were 8,522 results from when it started in 1975 to when we did the test in 2000. And remember, there was 1,000 possibilities. So we had roughly 8.5 times as many trials as we did possibilities. In this case, the chi-square test only gave us 42% confidence that it was the uniform distribution. For the Pick 4 lottery, it started only in 1977, so we had fewer results. We only had 6,500 results. And there are 10,000 possibilities. So we had fewer results than possibilities, and the chi-square test gave us no confidence. So here we have distributions on very big domains, and given samples of the distribution, we need to know various things about it. We might want to know the entropy, the number of distinct elements. We might want to know something about the shape of the distribution. Is it monotone? Does it have like a single hump? Is it bimodal? Is it close to uniform? Is it close to a specific Gaussian distribution? Does it have this Zipfian characteristics? And we can't assume anything about the shape of the distribution. We can't assume that it's smooth or that it's monotone or that it's a nice normal distribution. These are questions that are considered in statistics, information theory, machine learning, database algorithms, physics, biology, pretty much every scientific endeavor. And the key question is, how many samples do we need in terms of the domain size? In particular, do we actually need to go through the domain and estimate the probability of each domain item? Is it possible to have a sample complexity that's sublinear in the size of the domain? In particular, if we can get sublinear sample complexity, that would rule out the standard statistical techniques and any method of learning the distribution's probabilities on every domain element. So our aim in the upcoming segments is to see if we can get algorithms with sublinear sample complexity. All right, so our aim now is to see if we can find algorithms for understanding distributions using a sample complexity that's sublinear in the size of the domain. So we're going to look at the problem of detecting similarities of distributions. And there's lots of types of questions you could ask here. You might ask if two distributions, P and Q, are close or far. We're going to assume that P is given to us only via samples. The probabilities of P on every domain element are never written down anywhere. The only way we can understand anything about P is to push a button and get another sample. But Q, we can assume that Q is either written down, known to the tester. Maybe we can just assume that Q is a very simple distribution, such as the uniform distribution, so we don't even have to write it down. Or we might assume that Q is also given via samples, just as P is. So let's start with the simplest problem of testing whether the distribution P is uniform. So let's start with defining a notion of distance, the commonly used L1 distance. What it does is it sums over all domain elements, I equals 1 through n, the following quantity, the absolute value of P sub I minus what the uniform distribution assigns to I, which is just 1 in n. Okay, so we take those differences, sum up their absolute values over the whole domain, and that gives us our L1 distance. So what we're going to try to do is distinguish the case where P is the uniform distribution from the case where P is far from uniform in L1 distance. And it turns out this problem can be solved in sublinear time. In fact, square root the size of the domain. So we know you need that many samples. You need square root n many samples, and you can do it in some constant times square root n many samples. Okay, so we're going to go a circuitous route, and first I'm going to talk about the L2 distance. So in fact, this is the L2 distance squared. What it does is it sums over all I in the domain, something very similar to the L1 distance. Instead of looking at the absolute value of P sub I minus 1 over n, it's going to look at P sub I minus 1 over n quantity squared, and it's going to sum this up over the whole domain. Okay, now some very simple algebra. You just take this square term and write it out, and you get the standard P sub I squared minus 2 over n plus 1 over n squared, and then you break this apart into sums, and you get 3 terms. You get this one term, summation P sub I squared, that we're going to talk about in a minute. So what's this term here? We have this summation P sub I over all elements in the domain. So what's that going to be? P is a probability distribution, so the summation of P sub I over all elements in the domain is just 1. So this term is minus 2 over n. And what's this term here? Well, we're summing 1 over n squared, but we're summing it for I equals 1 through n. So we're summing it n times. So this is equal to 1 over n. So these two terms sum up to minus 1 over n, and together they give us this term right here. Okay, so now we have two terms. We have this minus 1 over n, and I'm assuming we know n. And then we have this summation P sub I squared term. What's that? That is a standard quantity called the collision probability. It's exactly the probability that you pick two elements from a distribution and you get the same domain element both times. Okay, so we know what that is. And the idea is going to be, we know 1 over n, we're going to estimate summation pi squared, and that's going to give us an estimate on the L2 distance squared of p from the uniform distribution. And that's how the algorithms are based. This is going to give us an algorithm for distinguishing the case where p is the uniform distribution from the case where p is epsilon far from the uniform distribution as follows. We're going to estimate the collision probability. That's going to allow us to estimate the L2 distance of p from uniform. And then we're going to use known and standard relationships between the L1 and the L2 distances to make conclusions about the L1 distance. Okay, there's still some issues remaining. The collision probability of the uniform distribution is 1 over n, so we're going to need a lot of samples in order to estimate it. But it turns out that actually root n samples are enough, because you can take order root n many samples and look at all pairs and see if they collide. So that gives us something like some constant times n many pairs. It gives us lots of pairs to look at. The problem is they're not all independent anymore, so we have to be careful in our analysis, but it works out and it gives us a root n sample running time. I should mention there are other ways to skin this cat. Paninsky used a completely different estimator. And it's fairly straightforward to see that you need root n samples in order to solve this problem. It's essentially a birthday paradox-like argument. You can't tell anything until you see some collision, and you can construct distributions which are very far from uniform, but you don't see collisions until root n samples. Okay, so let's go back to the lottery question. It turns out that when we did this test in 2000, we had plenty of samples to determine that the New Jersey Pick 3 and Pick 4 lottery really are drawn from the uniform distribution. We've seen that you can test whether a distribution P is uniform or not, and it's nearly the same complexity to test whether P is any other known distribution. Okay, so if you have any specific distribution, let's assume it's written down somewhere, you can test whether P is that distribution or far from it in pretty much the same way we did uniformity testing. with a little bit of added complications. Okay, so let's go to a somewhat different problem. Here, both P and Q are given via samples. Okay, so Q is never written down anywhere, and we don't actually know what it is. Now, you might use this if you're trying to see if there's a trend change in your sample data. And here, the way we're going to model it is you have two probability distributions, P and Q. They're two different boxes. Each time you need, you can press a button and get a sample from either one of them. And what we'd like to do is distinguish the case that P and Q are identical from the case that P and Q are far in L1 norm. And it turns out that this problem is quite a bit harder. We initially thought it should be root n samples, but it turns out that the complexity of this problem is actually n to the 2/3, so it's somewhat more. Why would it be so different? Well, it's fairly straightforward to show that collision statistics are all that matter. And when P and Q can be arbitrary, and in particular not so close to uniform, so if you have a pair of distributions where they assign identical probabilities to their heavy elements, but there's lots and lots of collisions there, and they have very different probabilities assigned to the small elements, then you won't see it because the collisions of the heavy elements are going to cloud everything up. All right, so we've talked about separating distributions that are identical from those that are epsilon far in L1 norm. What if you want to get an additive estimate on the distance? Or what if you want to get something a little bit weaker? I want to separate distributions that are epsilon close and from those that are 2 epsilon far. Is this something I can do? It turns out this is a much harder problem. You can still do it in sublinear time, but just barely. So here, you can do it in n over log n samples, and you need that many samples. It's a somewhat harder problem, but this is a very surprising result. It just came out in the last couple of years, and it's really taken the world by storm. How do the algorithms work? The algorithms use collisions to determine wrong type behavior. We already saw that in uniformity testing. But what they do is they use linear programming to determine if there's a distribution with the right collision probabilities and the right property. For lower bounds, we know that the collision statistics are the only relevant information that an algorithm could use. So because we're analyzing collisions, and collisions are not independent, we need new analytical tools. In the past couple of years, a new central limit theorem for generalized multinomial distributions has been developed. This powerful tool has already been applied in many new results. In the next segment, I'm going to talk about a number of other properties for which sublinear sample property testers have been devised. So let's turn to other properties of distributions that you might want to understand in sublinear samples. And two important quantities that you'd want to understand about your distribution are the entropy and the support size. The support size is the number of elements in the domain that have positive probability in your distribution. The entropy is an important measure of information that's widely used. One setting is to determine whether neurons respond to various stimuli. Each application of a stimuli gives a sample of a signal, and by looking at the entropy of this signal, you can determine whether the neuron actually responds to it. Another place where we are interested in the entropy of information is to determine whether the data is compressible or not. Well, is the entropy something we can estimate? In general, we can't even get multiplicative approximations of the entropy, but kind of for stupid reasons, and that's because it's very hard to distinguish a distribution which has all its probability on one element from a distribution that has all its probability on one element except a tiny, 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 tiny amount on a second element, because you're never going to see that in a second element. So because of that, you can't get a multiplicative approximation of the zero entropy distribution. But what if you knew the entropy was at least some constant? Okay, the entropy can be up to logarithmic in the domain size, so assuming it's a constant is just really assuming that there's some probability that it's on a second element. In this case, you can gamma multiplicatively approximate the entropy with just about n to the 1 over gamma squared samples. What that means is if you want to get a factor of 2 multiplicative approximation of the entropy, you only need n to the 1/4 many samples. And in fact, this is tight. We know that you actually need at least that many samples. You can't do better than that. We know that this problem requires n to the 1 over gamma squared samples in general, although there are some special case distributions where you can do better, such as when the support size is small. There are similar bounds for estimating the support size. What about additive approximations for entropy and support size? Turns out that here, again, we can get just barely sublinear. We need n over log n samples, but we can do it with n over log n samples. Lots of other properties have been considered. Some examples are whether a joint distribution is independent or not, whether a distribution can be succinctly described as a k-histogram distribution, whether a distribution is monotone, increasing, whether it looks like it's bimodal, properties of multiple distributions, are they all the same or not? It's an active area of research, so I hope I've convinced you that for many problems, we need a lot less time and samples than one might think. Many cool ideas and techniques have been developed, and it's an area of exciting research, so there's lots more to do. In the upcoming modules, you'll see some of these ideas develop further. Thank you.